This is the RunSafe Security Minute. We're here to provide 1-minute security briefs. Today's question is,
Mitch, highlight some fun problems to solve when you converted RunSafe code from C++ to Rust.
RunSafe code, also referred to as LFR, Load-time Function Randomization, recently underwent a transition to Rust from C++ in an effort to further improve the stability and safety of code that ultimately runs during your process's randomization. While it initially started out as simply reintroducing features in Rust, at a certain point, it became worthwhile to convert the remaining C++ to further take advantage of Rust language benefits, primarily memory safety. I will highlight two key parts of our transition to Rust. The first being memory unsafety around raw memory access. To truly benefit from the Rust implementation, it benefits us to try and avoid using memory unsafe constructs as much as possible. The C++ implementation of LFR directly interacts with the process's memory space via direct pointer manipulation. We wanted to avoid unsafe code scattered everywhere, so we collect all the available process memory in advance, adjust memory permissions, and retain byte slices of those sections of memory. This allows us to use those byte slices safely everywhere. These byte slices are additionally placed in a collection, which allows us the ability to query and find the appropriate slice for a given address. We further abstracted this memory interface for cases where we want to run the same code on a live process, or an ELF file, as we do for TRAP-v2 conversion. The sharing of the same code in multiple phases of LFR reduces the size of our codebase, improves the overall code coverage, and makes the single implementation more robust. Known good testing is the second key feature I'd like to highlight. While our test coverage is overall quite good, there are some small details that slip through the cracks when doing a re-implementation. To avoid these surprises, we wanted to make the re-implementation as accurate to the original as possible. The approach we took was actually to build and run both the Rust and C++ implementation in the same process, and compare the entire memory space of the randomized process with both implementations to make sure that we were getting byte-for-byte exact behavior. Any deviation was either a bug in the Rust implementation or incorrect behavior in the C++ implementation. With this approach, we were able to rapidly find any issues in the Rust implementation during the rewrite and add a corresponding test case. Those were the two key features I'd like to highlight of the Rust re-implementation. Thanks.